This is the second part of ethers, which is called epoxides, and epoxides are cyclic ethers, but I'm covering them separately so you don't have to be inundated with a long chapter. Okay, so epoxides are cyclic ethers, and the oxygen in this is specifically in a three-membered ring. So if it's not in a three-membered ring, it's not called epoxide. So for example, tetrahydrofuran, as we learned in the previous portion of ethers, is not going to be considered an epoxide. It has to be a three-membered ring. So simple epoxides can be named as oxiranes, but if it's a bigger system, then it can be called an epoxy, all right, because it's a very specific system. So then the naming can be epoxy. The common names are coming from the alkenes, all right, from where the epoxide is coming from. So for example, in this case, which is oxirane, the first one, which is the smallest epoxide also because you have only 2 carbons in this. This is also called ethylene oxide, ethylene coming from the fact that you only have 2 carbons in it, okay, and it's an oxide. So that tells you that you have an epoxide in there. Here is what we call an oxirane also, okay, because it's an epoxide. But now this is slightly different because you have a 4-carbon structure, all right? So the long chain is 4 carbons, so hence it's called butene. Now remember, this is all coming from an alkene, all right? So this is butene, and then they have the cis, which means that, of course, you have your hydrogens on the same side, and it's an oxide. Okay, so here this one, nothing to be scared of. This is cyclohexene oxide because the epoxide is on a cyclohexene ring. So that's how the nomenclature will work. Hopefully you won't get anything more complex than this. We're not really doing very much properties of epoxides because they're similar to ethers. Okay, so we're going straight into the synthesis. Now the synthesis is a little bit different than normal ethers because you're actually forming a ring. All right, in ethers you could take 2 components and join them together, but here you have to start with 1 component and then make it into a ring. So the very specific reagents that are actually used for this, and more commonly, these are known as peroxides or peracids. Okay, in these cases, very specifically peracids. So for example, right here, MCPBA, which is metachloroperoxybenzoic acid, MCPBA. Okay, so MCPBA, very common reagent for making epoxides. And I want you to look at this portion over here. If I remove this oxygen or this 1 oxygen from here, then this looks like an acid, carboxylic acid. But since we have an extra oxygen, this is called peracid. As we know, per means that you have the maximum number of oxygens present in a system. So this is going to be a peracid, and that's how you will see all of these also. These reagents, they all have an extra oxygen. And because of that extra oxygen, they're actually very good oxidizing agents, and they can readily give this oxygen away. So the simple synthesis for an epoxide is taking an alkene, whatever you want to start with, and adding the peracid to it, and that's how you get the epoxide. Now, one thing you have to remember about the epoxides, which is given on this portion here, is that since it's a 3-membered ring, it's a highly stressed ring, okay, because 3-membered rings are constrained by their bond angles. So it's a highly stressed out ring, which means that you will never get a trans ring possible, which means that 1 bond going forward, 1 going back is never going to happen. So which means that the epoxide ring, the oxygen is on the same side. Okay, so you have to be careful what you start with. So if you start with something that is trans, you will end up getting a trans relationship here also, and if you start with something that is cis, you will also get cis. Okay, the other thing you have to know is that if in case you're creating a stereocenter, then you will have enantiomers. All right, so for example, in this case, you will get enantiomers because you have no choice whether the reagent is coming from this side or it's coming from this side. In the next slide, we'll go over the mechanism, but still you don't have any choice of whether the reagent is coming from here or here, so which means it can come from both faces, and if it comes from both faces, you end up getting both kinds of epoxides, which means you end up getting a racemic mixture. Usually in exams or in homework, you don't have to write a racemic mixture. It's kind of understood. So all you have to do is specify the stereochemistry, and it's understood that you know that you are actually making an enantiomer. So here is the mechanism of this reaction. And the mechanism of this reaction is what we call concerted mechanism. And in a concerted mechanism, everything happens at the same time. There is no real starting point, although it's very easy to see that, you know, maybe this is electron rich or this is electron rich. But in concerted mechanisms, it's a little bit harder to judge, okay, where the electrons start from. And that's why when you look at all of these arrows, you have no idea which is the first one, okay? But essentially what's going on here is that in a roundabout way, in a concerted mechanism, the electrons are being transferred here to the oxygen. This bond is breaking, okay, and then this bond, these electrons get transferred here. These electrons get transferred here, which means you form a bond here. Now remember, here is the peroxy part, okay, here are the two oxygens. So then this bond actually breaks apart, and then this oxygen forms a bond with this carbon. So then here is this oxygen, which is connected to these two carbons, and you end up getting an acid at the end. So an epoxide and an acid. That is the mechanism. It's called concerted mechanism. For an exam purpose, you don't have to remember that, okay? I will just have you draw this, at least the stereospecific compound, okay, but not the mechanism. But I need you to know that it is actually a concerted mechanism. Okay, here is another way to make epoxides, and this is using the Williamson synthesis, and this is intermolecular synthesis. If you remember, we did Williamson synthesis back in ethers also, where you have a leaving group and you have a strong nucleophile. Now in those cases, in the traditional ethers, you were actually using two components. So you had an alkoxide separate and a leaving group separate, okay, or a substrate separately in two different compounds. Here it's going to be in the same thing, okay? So for example, you take a cyclohexene and you form a halohydrin using chlorine and water. And this is what you end up having. You treat this with sodium hydroxide or sodium, and then of course you remove the hydrogen from here. That's the acidic proton, and you form an alkoxide right here. So the nice thing about this group over here now is that you have an alkoxide as well as a leaving group. So that alkoxide will then attack this carbon in an SN2 fashion and then get rid of the chlorine, and so then you end up getting this epoxide ring. Okay, so this is like an internal cyclization to form an epoxide. Again, the epoxide that you will form now is going to be only one-sided. Now the nice thing about this reaction, you don't get a racemic mixture, you only get one kind. Okay, so that's the nice thing versus the peroxy, except for peroxy, if you are using a symmetrical compound, you don't have to worry about racemic mixtures. The reactions of epoxides are similar to ethers, which means that you can open up the rings. Okay, just like ethers, you can cleave them. You can also cleave epoxides. But there is one other thing that is very typical of ethers, of epoxides, is that they're very susceptible to nucleophilic attacks. And this did not happen in the normal ethers because there was no constraints. Okay, but here you have an epoxide, which is a three-membered ring, which is, as I said, highly stressed out ring, okay, because of angle strain. And so these rings become highly susceptible to attacks by nucleophiles. And so typically what's going to happen is if you have a nucleophile, you will have the nucleophile attacking one of the carbons, and we'll talk about which carbons in a minute. But you'll have the carbons, the nucleophile attacking one of the carbons, and then you'll have the ring opening. That oxygen will stay on, and of course, in the second step, you will protonate the oxide, and you'll get up an alcohol. So invariably, for all epoxides, you will see an alcohol group and then the nucleophile on the other carbon. Which one goes where is something that we have to talk about. If it's symmetrical, it doesn't really matter, okay? But if it's asymmetric, then we have to discuss that. But one thing is pretty standard, that if you have an epoxide, you will invariably get an alcohol and you will get the nucleophile on the other carbon. The other part that is very interesting about the nucleophilic attack is that the attack is backside attack because it's a nucleophilic, so it says SN2. This is not SN1 reaction. So because it's an SN2 reaction, the product that you end up getting is going to be trans, okay, or anti, as we say, which means they're opposite from each other because the nucleophile attacked from behind, okay, from the opposite side. So the first ring opening that I want to look at is the one for in an acidic medium, and you were using water as a solvent. So here is the acidic medium, you have H+, here is an epoxide ring, and you open this in presence of acid and water, and you end up getting two alcohols. Now I want you to note the stereochemistry of the alcohols. It's actually anti, so which means they're opposite on each other, and we'll talk about how we get that in the mechanism. If you don't want two alcohols and you want to get one ether, you can just change the nucleophile a little bit and instead use alcohol instead of water. Okay, so now remember, we just said that in the previous slide that all of these ring openings are nucleophilic openings. Okay, so which means there has to be a nucleophile. How you promote that nucleophilic attack is a different thing. All right, so here the nucleophile is water, here the nucleophile is the alcohol. Again, these are on opposite sides, which means this is an anti-attack. So let's look at the mechanism of the reaction. Here's the epoxide. The epoxides are electron rich, and so they are the ones that will act as a base and pick up a proton from the acid. Okay, and so they'll become protonated, which means now you have an oxonium ion. Once you have an oxonium ion, now this is a good leaving group. Okay, and so here comes the water, or the methanol for that matter, and now this is a weak enough base that it can act as a nucleophile, or it is the nucleophile, and it will attack one of the carbon centers, okay, either this one or this one, and in this case both of these carbons are symmetrical, okay, which means they're equivalent also, so which means that this can come from either this side or that side. The important thing is that it is coming from the opposite side of where the epoxide ring is, because remember the epoxide ring is on one side. Okay, so it's going to come from the opposite side, which means that the ring opening is going to be on the opposite side also. Okay, so if the water came from the behind side, now this alcohol, the ring opening here was on the front side. Okay, and that's how you actually get the anti-stereochemistry here. And so then once the water has attacked, this is still an oxonium ion, and the water will come and pick up the extra proton from here, and here you have your diol. Okay, and so this is now a trans diol because of the way the mechanism worked in the ring opening. I want to bring a point here for you about the stereochemistry of all of these glycols, diols. And the fact that when we made it before, okay, this was how we made it before. We took an alkene, and if you treat that with osmium tetroxide or with KMNO4, you ended up getting a syndiol, okay, which means that the alcohols were on the same side. But what if you didn't want this? Okay, so now you have a different way of actually making antidiols, where you can treat that with per acid and then do a ring opening, okay, because that's always going to be an anti-mechanism. So one other thing to note about the ring opening, we talked about ring opening as far as giving trans products, which is anti-diols or anti-nucleophile and alcohol. But what if you have an asymmetric epoxide? So for example, if you have an epoxide like this, where one carbon is secondary, the other one is tertiary. So in that case, what you do is the nucleophile will then prefer to add to the more substituted carbon, and this is the more substituted carbon, so that's where the bromide will actually attack. Now this is specifically true for the acid catalyzed rings, okay, and so this product where the bromide is actually attacking the secondary carbon is not going to form. Okay, so you will form only one product, so you add the nucleophile to the more substituted carbon. Okay, that's how it works. There is a difference in the ring opening in acid versus base mechanism. When you have an acid mechanism, the first step is, of course, the protonation of the epoxide. This is not true when you have a base opening, okay? Because when you have a base attacking, it means that you just have a nucleophile attacking, all right? So which means that the oxygen here is not protonated. So in case of acids where the oxygen is protonated to give an oxonium ion, the structure of the epoxide is a lot different, and therefore the mechanism is a lot different, because this is a good leaving group here, you don't need such a strong nucleophile. If you don't need such a strong nucleophile, then you can get away with an SN1 type of mechanism, right? And in an SN1 type of mechanism, you need to have a carbocation that is a lot more stable, more like a tertiary. So tertiary is the most stable. So in case of acid mechanisms, you will find that the nucleophile will attack the more substituted carbon. In the base attacks, things are a little bit different. Okay, so now in a base attack, you have a strong nucleophile, and in this case, and if you have a strong nucleophile, it is more like an SN2 mechanism, and SN2 mechanisms prefer the least sterically hindered carbons. Okay, and so therefore the product will be slightly different. So depending on what kind of a product you want, you choose either the acidic medium or the basic medium. Okay, so again, remember in SN1 type, in acidic medium, it's more like an SN1 mechanism, and in a basic medium, it's more like SN2 mechanism. So you have attack at the less hindered carbon. So you have a choice of how you want to make your product. Here are some of examples of reactions of epoxides, and this is a nice slide because it just gives you a whole variety of reactions that are going on here. So I don't want you to get bogged down with the variety. I just want you to focus, okay, and focus on, say, for example, here is your starting material, which is a asymmetric epoxide, and that's another reason why I like this chart, is because you have a nice example here. So here is the more is the asymmetric epoxide going on. So here you have water, and remember we said that you will get a diol, and the stereochemistry is not shown here, but I know that you will know that it's actually an anti-attack. All right, so again you will see for all of these, okay, since the nucleophiles are not that strong or they're sterically hindered, they will actually go to the carbon that is less sterically hindered. All right, in this case here you can't even tell which alcohol came from the water, so it doesn't matter. But in an acidic medium, remember that you will always have attack at the more sterically hindered carbon, okay, or the more substituted carbon. So here this is kind of a nice chart to keep handy, okay, and so all the reactions are taking place here at the less sterically hindered carbon. Okay, all right. Ethylene oxide, which is epoxides, okay, just a three-membered ring, is a very good building block, okay, and this slide may not make any sense to you right now, but I still want to give it to you so that you have it handy, because as we go on with synthesis during this semester, you will see that we are actually building molecules, and as we build molecules, you will need to know how to add 2 carbons onto a system, and if you have to add 2 carbons, adding an epoxide is the best way to add on 2 carbons, okay, very easily, because you can have a ring opening with any kind of a nucleophile. So just go through this slide when you get a little time and see how the ring openings are taking place, okay, and at every time you're opening up, you add 2 carbons to the existing structure. The applications of ethers or as epoxides is kind of limited. Not limited, it is very common, but not in the sense that we talked about before as in solvents and all that, but epoxides are very common as polymers, and one of the most common polymer that you would probably recognize is an epoxy resin, and those are used pretty much as an adhesive to cover any kind of wood furniture or any kind of surface, because it's very, very resistant, okay, and it sticks very nicely to surfaces. And so you have an epoxy resin with a hardener, which causes a polymer to form, and once that polymer is formed, you're ready to coat it onto whatever surface, okay, and it makes a really very good polymer agent. So you have different kind of polymers, straight chains, and then you have cross-linking polymer also, which makes for very good surfaces. It really protects the surface. And that's pretty much the end of this chapter for ethers. Okay, so in this case, you should learn how to make epoxides using the peroxides, and of course learn about the ring openings.